The next topic is binary solutions in liquid solvents, and we'll first take up dissolution of solids in liquids. Now, this dissolution process for a solid X can be expressed as the change of X solid into X solvated. We're just considering water as the solvent in this case. Now, the solubility of the solid in a given solution depends on a number of factors, the primary factor being nature of interaction between the solid and the solvent. Now, as we should already be aware of, there's a general idea that like dissolves like. If it's an ionic compound, it will easily dissolve in a polar solvent. And if it's a non-polar compound or a non-polar substance, it will easily dissolve in a non-polar solvent. Like dissolves like is your go-to idea when it comes to checking solubilities of substances in a particular solvent. Now, if it's an ionic compound, then solubility is expressed in terms of solubility product, or KSP, which has been dealt with extensively in the chapter Ionic Equilibrium. Now, for this process in which a solid is converted into an aqueous solution, entropy change for the process is always positive. Enthalpy change, on the other hand, could be positive for endothermic dissolution, or it could be negative as well. Now, for the specific scenario in which enthalpy change is negative, we have a scenario where delta G naught for this change will be negative, because delta H naught is negative and delta S naught is positive. Since delta G naught is negative, this means that this solid will be soluble in the liquid at all temperatures. In a second scenario, delta H naught could be positive, it's an endothermic change, and delta S naught is positive as well. Now, delta G naught, which is delta H naught minus of T delta S naught, has two different terms to it, of which the second term with sign included is negative and the first term delta H naught is positive. Now, it's fairly evident here that when you increase temperature, the second term will become more and more negative, which means delta G naught becomes more negative and solubility increases. We also have the same result when we consider equilibrium constant for a process which is endothermic in nature. For an endothermic process, as you increase temperature, the equilibrium will shift forwards. So we can say that solubility will increase. Now, if it's an exothermic change, as in the case of case 1, then we get two different pictures from an assessment of the equilibrium constant and when you take the general expression of delta G naught into account. Now, the general expression of delta G naught gives you the second term as negative and the first term delta H naught as negative as well. And when you increase temperature, the second term seemingly becomes more and more negative, which should make this entire process more spontaneous. However, if you consider the result from equilibrium's perspective, then for this exothermic reaction, as temperature is increased, the equilibrium would shift backwards. That is, solubility will decrease. And this is the actual result that we get at the end. For a solution which dissolves in an exothermic manner, as you increase temperature, solubility decreases. Now, those who've attended lectures on thermodynamics already know the reason for this. Anyways, in any case, when you want to decide the increase or decrease of solubility, it's the equilibrium concept which is your go-to concept. That's where you will not go wrong with this. Now, when you want to evaluate the vapor pressure for this scenario, that is when a solid has been dissolved in liquid, then it's found that vapor pressure of the solution is less than vapor pressure of the pure solvent. Dissolution of a solid in a liquid results in lowering of vapor pressure of the solution. One of the ways in which you can clearly imagine this or easily imagine this is if you consider the homogeneous mixture in which you have a liquid, and it's a closed container, so vapors can build on top of the liquid. Now, in this case, if you dissolve a small amount of solid in the liquid, then a portion of the surface area of the liquid is taken up by solute particles, which I've marked as cross. The dots are the solvent particles which are present. Now, because a portion of the area of the surface is taken up by the solute particles, this means that the rate of vaporization now is decreased in comparison to the vaporization which could take place before you dissolved the solid in this liquid to make the solution. However, the rate of condensation remains unaffected for the pure liquid as well as for the solutions, because condensation will take place over the entirety of the surface, but only a fraction of the surface can now be utilized for the vaporization process. As a result, compared to a pure solvent, the relative rate of vaporization is now lower. So the concentrations of vapors that will build up over the liquid surface will be lower. Hence, we have a lowering of vapor pressure when a solid is dissolved in a liquid. Now, the next binary solution which we will pick up is the solution of a gas in a liquid. I think this will be a very common and intuitive idea that if you have a liquid in which you're trying to dissolve gas, then as you increase pressure on the system or pressure of the gas on the liquid surface, then more and more amount of gas will enter into the liquid. That is, dissolution will be to a greater extent, or solubility of the gas goes up. So an intuitive idea here is that the solubility of a gas will increase if you increase pressure of the gas on the liquid surface. Now, quantitatively, this is expressed as a law called Henry's law, which states that, please write this down, Henry's law states that the solubility of a gas in a liquid is directly proportional to pressure exerted by the gas on the liquid surface. Alternatively, we can also say that, in fact, this is how the mathematical expression for Henry's law goes. It states that the mole fraction of the gas in the liquid is directly proportional to pressure exerted by the gas on the liquid surface. Now, P is directly proportional to xi. From a causality point of view, I think it should be written in the opposite manner. From a causality point of view, we should write that xi is proportional to pressure. That if you increase pressure, then mole fraction of the gas in the liquid will go up. But the original expression of Henry's law expresses this, that P is directly proportional to xi. In fact, P is taken as Kh into xi, where Kh is called Henry's constant. Now in this case, Kh depends on nature of interaction between the solute, which is the gas, and the liquid, and it also depends upon temperature. Now, when we are talking about two different gases and we want to compare the solubilities, or we want to compare the Kh values, then we will compare their solubilities at fixed values of pressure. Now, in the equation P is equal to KH into Xi, if you fix the pressure, then Xi will be greater, or solubility will be greater when KH is less. So we can say that for a mixture which has lower value of KH, solubility is higher. Now, if you want to evaluate the same gas at two different temperatures, then it is easy to show that if temperature is increased, solubility will decrease for gases. It is not always true for other scenarios, but it's always true for gases. Now, a very simple way of looking at it is this, that if you have gases dissolved in liquid and you start heating the solution, then temperature increases and the kinetic energy of individual particles will try to increase. Now, when gas particles which are dissolved in the solution get higher kinetic energy, it becomes easier for them to escape the liquid and go back into the gaseous phase. So, an increase in temperature will decrease the solubility of gas particles which are dissolved in a liquid. Now, a thermodynamic analysis of this part will also give you the same thing. Now, the first thing in our thermodynamic analysis is that any dissolution process involving a gas is only possible if the dissolution is exothermic in nature. Now, when you're dissolving a gas G in, let's say, water to make an aqueous solution, this is a process for which delta S naught is negative, because the extent of randomness which a gas has is decreased when you dissolve it in a solution. And if you evaluate delta G for such a process, which we're writing as delta H minus of T delta S, then the second term, including the sign minus of T delta S, is already positive. If you want dissolution to take place, you want delta G to be negative, or delta G naught if you're taking it under standard conditions. You want it to be negative, which means delta H has to have a negative sign. And the negative sign has to overcome the effect of minus of T delta S. Only then is it possible that delta G will be negative and dissolution will be spontaneous. So any scenario which involves dissolution of a gas to make a solution is possible only when exothermic dissolution takes place. Now, when we want to evaluate the effect of temperature, we look at this equation, delta G is delta H minus of T delta S, and at the second term, second part, which is minus of T delta S. Now, in this case, if you increase temperature, minus of T delta S will become more positive. If it becomes more positive, delta G becomes less negative, which means it becomes less spontaneous. Alternatively, you can also arrive at the same result if you consider that this reaction is exothermic in nature. So for any exothermic process, if you increase temperature, the equilibrium constant decreases, equilibrium shifts backwards, and solubility decreases. Now, when solubility is lower, it also means that the value of KH is lower. So, just to wind up a little, KH, or Henry's constant, depends on nature of interaction between the gas and a liquid. So if you have different gas liquid couples, you'll have different values of KH, and the solution and the mixture for which solubility is higher will be the mixture for which KH is lower. In a different case, if you are considering the same mixture, same couple, so that KH is fixed, and then when you're changing the temperature, then as you increase temperature, the solubility of a gas will decrease, and so KH decreases as well. A plot of P versus I gives us a straight line which has a slope of m equals kh. This you get from the equation P is equal to kh into xi. Now, different gases will have different values of kH, so slope of this graph will depend upon the gas and solvent mixture which is being used. Now, Henry's law finds applications in industry and also in several biological phenomena. One of the most common scenarios is the dissolution of carbon dioxide in water to make carbonated drinks. Now, carbon dioxide is dissolved in water at high pressure and at low temperatures, so that a lot of carbon dioxide can be bubbled into it, which gives you that sparkling effect. When you open a bottle of carbonated drink, it gives you sparkles, gives you a fizz. And that's because when you open the bottle, the pressure on it gets reduced to atmospheric pressure, which decreases solubility, and you have bubbles of carbon dioxide forming on the surface of the liquid. Similarly, when scuba divers dive to great depths, they have to deal with high pressure acting on them at those depths, because of which there is an increase in the amount of gases which dissolve in their blood. Now, when they are raised back to the surface and the pressure on them gradually decreases, these gases which were previously dissolved now start forming bubbles, and they get desolvated from the blood, which results in bubbles, mostly of nitrogen bubbles, forming in capillaries. There's a blockage of capillaries because of this, and it's called decompression sickness, and the painful experience are called bends. Now, to avoid bends, scuba divers have their oxygen supply uh, with some helium added to dilute the effect of nitrogen. Now, helium is very less soluble in water. So even at very high pressures, the solubility of helium remains relatively low. Another application is when we generally move to higher altitudes, or when climbers go to higher altitudes, the partial pressure of oxygen there in the atmosphere is very low compared to ground levels. So that leads to lower oxygen concentration in the bloods of people in those high altitudes. This causes us to feel dizzy and to feel weak. This is a condition called hypoxia.